today we have Joan answering our questions on black holes, but I'll let him introduce himself. Thank you.
Thank you. Okay, so thank you to the science room people for organizing this. I'm Joan, and I'm doing a PhD in string theory, actually, but today I will talk to you about black holes. So essentially the main question that we want to answer at the end is, what is at the bottom of a black hole? Okay, so we'll do two parts, and then in the first part, okay, so as I said, I will talk about black holes, and essentially a black hole is a region in space where whatever that gets in, it cannot get out. It cannot ever get out. So no matter what happens, when something falls in, it will never come out. Okay, so we will see this more in the second part, but in the first part I want to focus on, okay, so we have this object in space out there in the universe, which has this property, but how is this possible? How can this possibly form in nature? Okay, and that's the first part of the talk, what I will focus on. Okay, I want to say, if something is not clear or you have a question midway, feel free to stop and ask me, just say Joan or something or whatever, and stop me. Then we discuss, and then I continue. I prefer to just get halfway of what I want to say, what that you understand, rather than explaining a lot of things and you don't understand anything. Okay? Okay, so, so how are black holes formed? To understand how black holes are formed, we need to know how stars are formed and how they evolve. Okay, so for star formation, so the universe is massive thing and it's mostly empty, right? Okay, there are some planets and stars here and there, but it's mostly empty. So it's empty space with some dust. At least a long time ago there weren't that many planets and stars, so it's just empty space with dust. When I say dust, I just mean atoms, so like hydrogen, some helium, and that's basically it. So we just have atoms lying around in space. Okay, actually the composition of the universe is almost everything is hydrogen, so it's like 70% hydrogen. Then we have about 30% of helium, which is just like the next heaviest element, so just two atoms together. And then there's nothing else. Of course, we're surrounded.
Is there deuterium?
Sorry?
Is there deuterium?
Yes, but deuterium is not stable. So it's mostly hydrogen and helium in the universe. Deuterium will fall into hydrogen. So, of course, we're surrounded by heavy elements, but we will see later how they form. So, as I said, the universe is mostly empty space with dust, which is this hydrogen and helium, and then this dust is moving around, just randomly, and then at some point it starts gathering, so becoming more dense at some point. And then gravity, in this point where it gets closer and denser, gravity starts acting, and then it starts pulling. So this hydrogen and everything starts forming kind of clouds, and these clouds look like this. So this would be like pictures of the universe. All the pictures that I will show today, except 2 or 3 which are obviously cartoons, all the others are real telescope pictures, so this is really how the universe looks like somewhere.
Does it actually look like that, or is that just a lot of wavelengths put together at the top of one?
No, it actually, okay, these are some pictures put together, but I think these are just patches put together, but the actual picture looks like that.
Okay.
Yeah. So as I said, we have dust, and then the dust, yeah.
Could you speak a little bit louder?
Yes,
My ears
I can
are
try
very
that.
blocked, I've got a cold and I actually can't hear you.
Okay.
There are people over here too, but good luck.
I'm just a bit deaf today.
Okay. Okay, so the universe is very empty, and then there's some dust, and the dust gets closer and forms this kind of clouds. So these are the clouds that we can see in the universe with the telescopes. So this cloud is essentially hydrogen and also some helium. Okay? So it gets denser, you can pass this around. So it gets denser, and then we have this kind of clouds, which is just areas where the dust is more dense. This is another picture. This is, okay, there's some stars there, this is another galaxy, and this red thing is another big cloud of dust where stars are forming. Okay? You can also pass this around. And I have another picture here of another galaxy. And also here, every time you see something like that, which is just some color, red or yellow, like that, this is dust that is collapsing and forming. You can also pass this around. Okay. So we have the dust. It collapses into clouds, and then within the clouds the same thing happens. So inside the cloud, there are some regions where it's more dense, and then this becomes more and more compact. So when that happens within a cloud, we start having what's called a protostar. So this green thing, everything is a cloud, and then somewhere in this cloud, it gets denser. So it forms like a ball of hydrogen and helium, and this ball is what will become the star. So we have what's called a protostar, which, okay, I'll pass this around now. It's just like a small ball here. The dust forms clouds, and then the clouds form these balls, and these balls is what will become the stars. So now we just have a very, very dense ball of mostly hydrogen, okay, which keeps getting denser and denser. And then, as it gets denser, it also gets hotter. So we have this massive ball.
Here, yeah.
Forget about this for a second. So we have a massive ball of hydrogen, which is very, very hot, and it keeps getting denser and denser. And then once this happens, the center is so hot that at the center of the star, heavier elements than hydrogen and helium can be created. So the nucleus starts fusioning between them, and then we get heavier elements. For a star that is very massive, we will have a structure like that. So we will have all the outside will be hydrogen, and then just at the center, at the nucleus, we will have heavier elements, and then the heavy elements that can form inside the star. So we will have hydrogen, helium, okay, some others. And then for very, very heavy stars, the heaviest element that can be created inside the star is iron, as we can see in this cartoon. Okay, so these two are cartoons, obviously. Yeah, and that's how you can pass it around, if you want. So we have, now we have the dust that collapsed into something, a ball, and then this ball starts getting hotter. And now this is the star. It starts creating the elements inside, and since it's so hot and it's creating all that, it's radiating a lot of light, and this is the sun that we see. So actually, our sun is one of these. So we have the cloud of dust. This is another picture, and then we have an average star, which would be the sun. And then, okay, the sun will evolve and something will happen. But the sun is just that. The ball of hydrogen and helium that created got a lot denser and hotter and started creating other elements. Okay, but today we are concerned about black holes. So to have a black hole, we need a star. We need to start with a very massive star. So the same thing that I said, exactly the same thing, but we have a lot of hydrogen and a lot of helium. So we have a massive, massive star, which is very, very dense and ultra hot. And then in these cases, we can form all these elements, and what will happen there is that, so we have all this fusioning, and we have with iron and everything, and then this star will expand at some point, and then the core, the nucleus of this, it will be so dense and so hot with all the elements that it will collapse. And then at some point this will explode, and this is what's called a supernova. So the star will grow, it will explode, we will have the supernovas, and then what remains at the center is what will be the black hole. Okay, so a supernova is something very, very bright. So we had a massive star which has created a lot of elements, and now it explodes. So this explosion is very bright. I'm quite sure it's the brightest thing observed by telescope. So this is a picture of another galaxy, but here you can see supernova exploding, so the light of the supernova. Okay. Yeah.
And also that, so when we kind of see supernova stuff on TV documentaries about science, they tend to be represented as like what we think of as an explosion as goes bang.
Yeah.
Is that actually what happens, or is it slow?
No, it's actually what happens. So
it actually flies out and like
for stars that are not very massive like the sun. Okay, so the sun will also expand. I'm afraid it will swallow the Earth. Okay, it will be a million years from now. And then after that, the hydrogen in the outside, it will just go away slowly, and it will have something else in the middle, which I will talk about today. But in very massive stars, yeah, it literally explodes. Yeah, so the center goes like that, and boom, yeah.
Okay,
Yeah. So we have this massive explosion, which as we have seen is very, very bright, and then this is what the dust after the explosion looks like. So of this massive explosion at the center, okay, we'll have a black hole, we'll get there now. But this is like the cloud of dust that is surrounding the black hole at the end, after the explosion. Okay, so let me say it again. we had the universe with the dust forms clouds, the clouds form stars, stars create all the elements, and then massive stars explode at some point. You have the supernova, that's what remains after the supernova, but in the center we will have a black hole. Okay, and this is how black holes are created in the universe. From massive stars, which collapse, explode, and then what you had at the center, which is where was all the elements, all the heavy elements, and where it was more dense, it's so dense that it creates a black hole. This thing that once you get in, you cannot get out, so that it eats everything. Even light. If light gets into a black hole, it cannot get out because gravity is too strong. Okay. I also wanted to say.
Sorry.
Yeah.
So after this explosion, you're saying that nothing can escape. Obviously.
Yeah.
There's sort of the time period where it's supposed to change from everything having gone in one direction to turning around and going the other.
Yeah. So there's. Okay. No. The way I see it is like you have a cutoff region, and within this cutoff region, okay, everything falls in, and this forms the black hole, and what was outside this cutoff region, it just explodes and goes away. Okay, but you can separate it quite well, this cutoff region. Yeah. Yes, so what I wanted to say is, in stars, as I said, the heaviest element that can be created is iron, but we are surrounded by heavier elements mostly, so all the other elements are created in supernovas. This is the only place in the universe where we have enough energy to create something heavier than iron. So for example, all the gold in the universe is created from supernovas, because it's when this explosion happens that there's a lot of energy concentrated there, and then we can have fusion of heavy elements and have the rest of the elements. Okay? So, right, so this is how black holes are created in the universe. Okay? So this is nice. I mean, we have some pictures. This is what our theory says so far, but we have a lot of telescope pictures and they agree with what we think. So this is how they are formed. Yeah?
How long have we known this?
How long have we known this?
Like, when was the first theory about black holes or supernovae, and when did we observe them?
Well, the first theory about black holes and the first theory about supernovas, I think they are quite apart in time.
Yeah.
Yeah. So let me. I think
an exact date.
Yeah. I know. So I think the Hubble telescope was early 2000s.
So we've only known about them for that.
Well, we have seen them since from that period. About black holes, we know since the 1900s. So as I was going to say now. Yeah. I think I'll go on and then we'll answer your question. Yeah. So
we see from time to time we can see a supernova in the sky.
Yes.
With the naked eye, isn't it? With the naked eye.
I'm not too sure. Yeah,
I think it was in 2004 that you could see a supernova in the sky if you really paid attention.
Okay. I'm quite sure if it's close enough, it's so bright that for sure you can see it. Yeah.
Of course, it was a very minuscule spot in the sky.
Yeah. Because supernovas thankfully happen far away from here. So,
Of course.
Yeah, but I see no reason why you should not be able to see one.
Wasn't it an Australian observer who spotted 13 of the 14 supernovas? With all these expensive telescopes and on top of mountains and that. They saw one supernova. This Australian guy saw 13.
With his telescopes.
With his telescopes. He happened to be looking at the right place at the right time.
Okay, well, that's lucky.
Well, no, that's intuitive skill, isn't it? They actually have the skill to look at the right place at the right time.
I will say that's mostly luck, because supernovas happen very fast, right? And we have galaxies all over the place. So how do you know that if you look now at that galaxy, you will have a supernova there and not that one? Because just by looking with the telescope, he can have no idea if a star is going to explode there or there. So, I mean, you need some insight, but if he saw that many, that's also part of luck, I would say.
Well, he's a very lucky person.
Yeah.
By the lotto. If there is a supernova, how long the light on the bright will stay? Because it's not like just a blip It will, like 1 year, 2 years, or how long it will bright?
I think that when it gets the brightest, that's like seconds, something like that. And then it will remain very bright for some years, I think. But that's just the brightest moment. That's very, very, very short, even in our standards. Okay. Julian?
How far is our planet to the closest black hole?
To the closest black hole? I don't know that. I know.
Isn't it the one? I don't know if it's confirmed already or not. The existence of a black hole in the center of our galaxy.
Yeah. So
that will be
according
responsible
to
for
the theory, we have a very, very massive black hole at the center of every galaxy. The thing is, I'm not sure if that's the closest we have or not. Maybe there's another one somewhere else. But yeah, at least at the center of our galaxy, there is a massive black hole, like a really, really massive.
Do they move? Do they get any closer to us, or we don't?
No, I guess if they move along with us, with the whole galaxy.
Should we take a break now? This is a good time.
Can I finish with
Yes.
one thing? Okay, so as I said, this is how black holes are formed, but this doesn't really give us an insight of how they behave or why the things that happen. So to do that, we need the theory, right? We can see all this with telescopes, but we need the theory to understand what is happening. So I will talk about this in the second part, but before I do that, let me just write, okay, I will not write any equation, I will just write some ideas, but let me say, black holes are described by Einstein's theory of general relativity, which was discovered in the early 1900s. So, and essentially, what this theory says is that the shape of space is related to the matter in the universe. Okay? So what this means is that we put a cloud of dust here, what I explained before, and then we make it, it collapses. All this is described here, so we have the cloud of dust, it collapses, it forms the star, it explodes, and then the shape that we have at the end is a black hole. Okay? Right. So this is all good, we have the observations, we put the matter here, we observe what happens, it's well described by this, and we get a black hole. Now, as a theorist, we like to do things by hand, so all this, the calculations in this, to match the observations of telescopes, they have to be done with computers because they are very difficult and very, very long, and okay, you need a computer. But as a theorist, we like to do things by hand. So to be able to do things by hand, we usually simplify things to look at an easier case. So now imagine what happens if we take this equation and instead of putting in the side of the matter of the universe all the dust and the hydrogen that forms the star, we don't put anything. We just put 0. So we have that space is empty. There's absolutely nothing. Just as before, we had that when we put the dust, the solution that we get is a black hole. If we put that the universe is absolutely empty, so that there's not even one atom in the universe, and we solve this equation, the solution is also a black hole. So the first question that I want to leave you with is, if there is no atoms in the universe, if there is absolutely nothing, you just have space, but there's nothing, it's the vacuum. What's the black hole then? How can you possibly form a black hole if there's nothing to form the black hole?
Thank you, Joan. I think we'll have 14 minutes break because that's a nice round number. We'll come back at 12:45.
Yeah.
If we were discussing where the black hole be when there's nothing there. So, surely for gravity to exist, you have to have matter in order for them to attract each other. So you have to have something in order for there to be gravity in the first place. And surely a black hole is
So for me, the black hole is just shape. It's just geometry. You really don't need any matter to have gravity. Okay, if you don't have anything, nothing will fall because of gravity. Because gravity will still be there. Yeah, of course. I mean, if there were no things to there, we would not be there. There would be no one to check if there's gravity or not. So just putting you there, that's already something, and that already has some gravity effect.
That's totally like square.
So, yeah, I guess it cannot be really tested in vacuum. I mean, to be honest, this is very crazy, okay? The universe is empty, of course it's not empty. But as I said, the universe is mostly empty, right? Between a galaxy and a galaxy, there's nothing in the middle. So the best approximation to describe that space in the middle is this. So this is not that unrealistic in certain places.
Where is the AE?
The ether. Yeah. So that's the ether was like this substance that was everywhere, right? And that every body, every star, every planet was moving within it. But the ether theory was disproved. So ether doesn't exist.
Well, that's rubbish because I'm planning to build an AE for the receiver.
This is kind of what I'm asking.
I'm planning to build an
How do you
AE.
get
It's very,
so
very easy. So you're talking about one part of physics and then be like, oh, what about this? And then but that's like a whole different question.
So, analogy I understand, that's a bit like saying, is there a sound if nobody plays the
He was able to transmit
kind of song or something?
wireless
Is there sound without a
electricity
signal?
to a car, which you could run all day. Yeah, but it worked. I mean, he was so far ahead of his time. He makes our electric car stupid. And so backwards, he got it right first time. He could run 24 hours a day, 24 hours the next day, 24 hours the next day, without a problem. All he needed, to make money would be a license to receive it.
Yeah.
You know, like you have a license to receive television.
This item
People are so close-minded, they can see further than the end of their nose.
Yeah, I'm not too familiar with
There's a lot of potential.
work like the exact thing that he did.
Still not.
So the only thing I can say is,
He had two
yeah,
he was right between
More
there.
energy that you built, exactly. And then it went out as like sound.
And he had a receiver which is tuned into
So when the pen
yeah, of course. So
it's approximately 12
You've got transfer to sound and probably a little bit of friction.
Just he's always
percent
around
hot electricity.
It went into
Yeah, I think for like certain bandits, he does it even when he's you can.
There's general in charge of electricity. Yeah, he was able to light the light bulb.
Serious cake, yeah.
yeah. So what I want to say as well is what I described here and the rest of the theory. It's not like the truth. It's the thing that we have described closer to what we see. Of course, Tesla had some experiments and some things which were working really well, and yeah, maybe they don't fit in the things that people study or explain now because they still cannot understand them. That doesn't mean that they didn't work. They work, but we still don't fully understand them. The other thing I want to say is the ether. So whatever Tesla was doing and it was working, I would say it's not through the ether that we are both thinking, because that thing was disproved in another way with gravity actually. If ether existed, there would be some drag, and people did an experiment, okay, which you can believe or not. Okay. But if that experiment were to be true, then the ether is not true.
If you take a Tesla coil, right, you can put 12 Tesla coils round you multiply the energy, if it's 8 kilowatt one, and you've got 10 coils, you've suddenly got 100 kilowatts.
So, do you know about this radio show?
You don't get something for nothing.
Do you know about the radio show thing?
It's square thinking.
Are you...
Of course. The only thing I'm saying is, okay, we don't understand.
We must be,
Yes. I wasn't involved. So
The only thing, exactly. So the only thing I want to say is, I agree with you. It has to come from somewhere, but I don't think it's coming from the ether, because the ether, at least as we understand it, maybe there's another kind of ether, and that's really what's there. But with the kind of ether that it was historically existed, that one exactly, it doesn't exist. Maybe it's something similar, but it's not that.
I just feel like
Because there are other experiments that disprove that. So Tesla's work, what he did works, and maybe there is something there that we don't understand. But that's something that we don't understand. It cannot be exactly what we are saying, what we are calling ether. It has to be maybe something similar, but a bit different.
I could
You've
talk
got
about it like,
resonance as well.
like say Imagine.
Yeah, but again, you don't need the ether
if you're
to
listening in the phone, get a lighter.
And a diffraction grating.
You know, I mean, if they go to television, they use the resonance technology.
Yes.
I guess so.
And they're much more efficient.
Yes.
You know, these plasma TVs soak up energy.
Yeah, I agree with that. Yeah. So I'm not saying none of these things. I think all of this is true, and it all exists. And we are not able to describe it, and we don't know how to describe it. I just wanted to make clear that it cannot be with the theory that people conjecture of the ether, because that one was disproved for other reasons. So there's something there that we can understand. Yes, I believe that. But that's something. Yes, of course. So the only thing is, I don't like the word ether because it's related to other things that we also believe, and these things have been disproved by other experiments. So there's something that we don't understand. Yes, there's something in there that we don't know how to describe. Yes, what's that? I don't know.
But they try to make it.
That's my fault.
What happened in Turkey is that we observe throughout the millennium, we observe, we try to fit theoretical models.
And now we know radio is not
we see that the extrapolations
just idiots
occur
like us.
pretty nicely. But still, they aren't always the dry truth, the general truth, because all of the models, all of the theories has an empirical background with an explanation, theoretical explanations of cause and effect that try to fit into the observations and extrapolate nicely.
Everything you
Yeah, exactly. So all that physics is observing the universe, seeing what happens, and then finding an equation or something that describes that the best that you can. If it describes everything that you see, okay, we believe that theory. Maybe someday you observe something else, and that something is not described by your theory. Okay, so then you invent another theory, which explained everything that the old theory explained, and it also explains the new things. And
It's like the classical mechanics developed by Newton. It was and it was very good at the time, but it was just an approximation.
Exactly, and there were things that could not be explained, and these explained them, and it also explained
we
everything that
iteratively
Newton.
adapt and refine our models, our explicative models.
Yeah, exactly. Exactly.
At the time it was either that tried to, it was a model of either that tried to explain many of the observations and try to correlate the observations of our universe, but then I believe we refined that model to be able to encompass
we don't know
new kinds of observations that were more in the previous model.
Yeah, exactly. There were, maybe I can explain later what things were not described by.
Yes. Cool. Are you happy?
Yes. Can I have another paper?
Yeah, sure. Just you could just like put this. Let's take it out.
the answer you gave
Yeah, that's a great idea.
we were able to like British therapy, holistic, natural
Excellent teamwork. Great.
It's an academic context. Yeah, that's really enjoying.
But like now
Okay.
I hate that.
Yeah,
Yeah,
okay.
why
Stuff
are you
with
including
different
this?
yeah.
If you're not, if you're doing it for
Lovely.
listening, it must be
Okay, everyone. Thanks for the lively discussion you've had. We'd now like to hand back over to Joanne for the second part of this talk.
Okay, thank you, Joan. So, with the question that I left you, if there's nothing, how can we still have a black hole? So for me, a black hole, even when we have matter, it's just shape, it's just geometry. So you can have nothing in the universe, but you can still have a black hole. Okay, to make this more clear, let me explain a bit. So this second part will be more theory-based, so with the equation that I brought before, Einstein's equation. So this equation describes black holes and it explains other things, so it's the theory of gravity that we use. But another thing that it says is that space and time are described in one single thing, which is called space-time, right? And then this space-time is something which, when you put something which has mass, it bends this space-time. And this bending is what will create gravity. So this bending of space is a bit hard to understand in 3 dimensions. So 3 dimensions as in 1, 2, 3. So imagine that instead of being in 3 dimensions, we were in 2. So you've probably seen this picture before. Okay. My drawing skills are not very good, but we have something like that, and this is like a sheet or like this paper. So the surface of this paper would be where we live. And then so we would be on top of this. And then this is everything. So just 2 dimensions. Okay, that one, that one. Okay, so what the theory says is that when we put a body or a star or a planet which has mass from here, or anything, even me, what it does is that it bends this space-time. Okay, so we put something, and then what will happen to the space-time, so to this thing that I drew here, is that it will bend around it. As I said, my drawing skills are not the best, but I hope this can be understood at least. So we had like a paper or something, which was the space-time, and then we put something. Okay, this is not bending, and then it will bend like that. Okay, so once we have this bending, understanding gravity is very easy. We have this, which is now bent towards the middle, towards this big thing. This could be a star, and then we put now a smaller ball here. So this smaller ball will be lying around comfortably in space, in this surface. But since this surface is bended, this ball will roll down towards the massive ball, right? So this rolling down towards the massive ball, this is how Einstein's theory explains gravity. So this is just the pen rolling down to the earth. And that's how we explain gravity. Okay? So now that I have this, it's very easy to see what a black hole is in this case. So instead of drawing this surface like that so that you can see, let me just do it like that. Okay, so this is the surface. If we were looking from top, we would see this or that. If we put up an object, a ball, in this space, so the space will get bended, right? Okay. So now, what a black hole is something so massive which essentially breaks the space-time. So we have that, then it goes down like that. So, as I said, a black hole is something that once you fall in, you never come out. So you're here, you're fine, you're here, you're fine. Once you fall, you're gone. You cannot come out. In this case, you could fall, stay here for a bit, and then you come out. Okay, that's fine. But in a black hole, you fall, and then you're gone forever. Okay?
And we have already a huge difficulty to get out of Earth, or out of the planet Earth, like
exactly.
Missions.
But so
we spend so much energy trying to
to escape. So imagine something so massive that, as I said, not even light can escape.
Yeah.
So in this case, you have some light here. It falls inside the black hole. It's gone. Okay. Where? Okay.
Does this only work in 2D?
No. This works in 3D. I did this in 2D to be able to draw it, because I cannot draw like a sphere,
Yes.
and then bend the sphere inside.
Yeah.
I cannot
But
draw
then if it's so very deep, how do you see that from the other way up? You know, it must collapse in on itself rather than to somewhere.
Yes, we'll get there at the end of the talk. Yeah, okay. So now that I have this drawing, it's also very easy to see what a wormhole is, which was another question. So, wormhole, once you are here, it looks very similar to a black hole, but actually what happens with a wormhole, okay, and now give me a second, because this is easy to draw if you know how to draw, but if you don't know how to draw, and it's a bit tougher. Okay, so this is our space-time. That's the space-time. Okay, I'm just doing the squares to say that this is like flat. Okay, and here it's not flat. So a wormhole, once you are here, it starts just like a black hole, right? So you're in space-time and then you start falling. But the difference between a black hole and a wormhole is that in the wormhole you will end up going out somewhere else. Well, this is more like space travel, but like teleportation, if you want to say. So maybe if you want to walk from there all the way up to there, it will take you, I don't know, 4,000 billion years. Maybe if you fall through here and survive, it will take you a day. Something like that. So this is like a shortcut. Okay, so the shape of the black hole and the wormhole is very similar, but the only difference is that with the wormhole you end up somewhere else, so you can go out somewhere. Okay. So, okay, this is nice. This is a black hole, but it's a bit hard or weird to think of a black hole like that. So when I think of black holes, usually what I think about is a sphere. Not that. So this sphere that I drew, it's just a surface, it's nothing, and this is called the event horizon, which I explain in a second what it is. And then at the center we have a singularity, which I will also say. So the event horizon is the point of no return. As I said, in a black hole, once you fall in, there's no way you're getting out. So this is the borderline. This is the line one. If you're here, you are okay. You can still get out. But once you cross this line, then you will fall. And there's nothing you can do. Even light. If light is around here, it's okay. If light crosses, it will fall. And that's it. Okay.
Mathematically, is it a approximation or is it a threshold?
Mathematically, it's
the notion of the event horizon.
No, it's a threshold.
It's a threshold.
Yeah. Yeah, there's no approximation. It is exact. So, black holes have not been directly observed. Up to a couple of years ago, we only knew about them, like they existed, because stars and planets moved in the space, and it only makes sense the way they move if black holes existed. And from a couple of years ago, we also have the gravitational wave detection, which I could explain later, or maybe not. But we have computer simulations of black holes, and this is what a computer simulation of a black hole looks like. Okay, you might recognize this as a screenshot from Interstellar, and it is a screenshot from Interstellar. But, so, the thing is, for the movie, they did this simulation of the black hole, and it's the best simulation of a black hole that exists. So before that, we didn't have a simulation that good, I think, because people didn't have enough money, so Hollywood said, yeah, sure, go on. And they did a massive computer simulation, and they got this. And they actually published papers on this, on how the light exactly bends around it, because it's the first thing they found something so like exact according to the equations. Okay.
Joan?
Yes?
If this is too off topic, then you don't have to answer it, we'll talk about it after. The line through the middle, I assume, is Hawking radiation?
No, I think that light is just light that is going there, and then light goes very fast, right? So instead of falling in, it just keeps going around. So light was going like that, and this is very massive, so it gets attracted. But
So why would the light not be coming from the same direction and coming out the same direction? Why would it not be coming out and then from the direction?
In that picture.
Or is that Hawking radiation?
So no, I don't think that's Hawking radiation, but also that black hole is probably spinning, right?
Okay, that makes
sense. So the light is probably just like,
sure.
Yeah.
That makes sense. So do scientists still think that Hawking radiation exists? Is that still a common theory?
Yes,
or?
this is still a common theory.
Okay, so how come it wasn't included in the simulation?
Well, it's probably included in that simulation, but Hawking radiation is something very, very weak.
Oh, okay.
So the time for a black hole to evaporate for Hawking radiation is ultra long.
Oh, okay, that's fascinating. Cool, thanks.
Yeah. So even there are probably black holes from the start of the universe which are evaporating and they still have not evaporated. It's that slow.
Wow, that's amazing.
Yeah. Okay. So, so this is the way I understand the black hole. The event horizon is this area here, it's this point of no return. And at the center we have a singularity. What's the singularity? Okay, I don't know. I can say some things later, but for now we are using Einstein's theory, and with Einstein's theory, I don't know. It's this thing that falls infinitely. It's basically an infinity. We don't know what it is. Okay, so to answer another question that was asked. There's a picture to understand this. Okay, you can say, okay, so we're in space, we are somewhere. By the way, this is not something that you can see. Okay, if there is light, it will bend around, but if there's no light, there's nothing in space here. There could be an event horizon here, and I would not see it. And if I cross them, too. But yeah, so this is somehow a bit weird, right? A region of space where once you step after a certain point, you fall. But then there's a picture to understand this. And it's like, we can understand this. Imagine that there's a river, right? And you're swimming in the river. You're swimming in the river, yeah? Okay, so we're swimming in a river. And we're happy, and we're fine. So there's this river, and we keep swimming. Yeah? We're happy, and we're fine. But now imagine that this river stops being nice. And then at the end of the river, there's a waterfall. Yeah, so we're happy, we're fine. But then once we cross this line and we start falling, yeah, we can be Michael Phelps or whoever, we cannot swim up a waterfall, right? So this point where we start falling, this is the point of no return. So in this picture, this line would be the event horizon. Okay, so this is the picture that is sometimes used to explain black holes. This region of space that you can escape is because it's like you're in a river, you cross the event horizon, you fall into the waterfall. You can try to swim up, you will not manage, you will fall. So in the question that was asked, it said if space-time literally flows into the black hole and it disappears, so that's not true. Space-time is just there, and then you can fall, and you fall inside the black hole, but space-time is not falling. Maybe the question was related to something else, which is when you do numerical relativity, like you put it in the computers, your space-time actually gets swallowed by the black hole and it disappears inside there. But that's just an artifact of the program. That's not something that is really happening. It's just the way that it's programmed, that's what happens, but that's not what is really happening in the universe, if all this is true. Okay, yeah, so that's the picture, and then I can go back. Okay, so the black hole. Now we know what the black hole is, or what the event horizon is. So what happens when we fall inside? Imagine that we are there, we are happy, and now we are here, and we start falling. So, as I said, once we get in, we cannot get out, so we will fall into the singularity. I'll say that more clear later. But essentially what happens is that inside the black hole, gravity is so strong that just the gravity pull that you feel in your head is much stronger than the gravity pull that you feel in your feet. So what will happen is that, well, you will get taller for sure, Yeah. Actually, your head will also get taller. Yeah. Once you start falling, at some point, gravity is so strong that you will break. So your head will be there. There will be your body, maybe a feet, maybe another feet. There's one arm. Maybe the other arm is gone already. After that, you will be some guts, still falling to the black hole. Yeah. Afterwards, those guts will also be destroyed, and you will have just some atoms falling into the black hole. And then you will fall into the center. And what's in the center? Okay, we'll see now. But yeah. So essentially, I think there was a question asking how does it feel to be spaghetti sized in a black hole. So my answer would be painful. It's very painful. You just get stretched until you break, and then you break more, and then you get disintegrated. Yeah. Okay. So
You're not a biologist.
Yeah.
Is the gravity strong enough that atoms would also be spaghetti-sized?
So if when you say atoms you mean protons, then yes. The protons will break into each component, which are quarks. What happens after that, no one knows.
Wow.
Do you have the situation where the electron, like does the strong force will be forced to come overcome by the gravity at some point? Like not just with the protons, but like to the electrons in the atom leave the nucleus, or does the nucleus break apart as well?
Yeah. So the nucleus will break there at some point.
And the
But
electrons, do they stay with the protons at some point, or do they?
no, the protons will also break into quarks.
Electrons.
Sorry. No. So electrons will.
Yeah, they'll
stay electrons.
Do they leave the? At what point do they leave the nucleus? Like,
At what point?
At some point.
Yes.
It's kind of like quark soup.
Yeah.
Much quicker because they are atoms are easy to unite compared to fission.
Yeah. So that also the other thing is that inside, once we start falling inside the black hole, we start having quantum effects, and I have not talked anything about quantum effects because all of Einstein's theory is classical. So the quantum effects that happen inside, we don't know, but we really should understand them to say what is exactly happening. So the best thing I can say is we don't really know what's happening inside. To understand what's happening inside and what's this infinity and all of that, we would need quantum theory of gravity, which we don't have. I work in string theory, so I will say that the best candidate that we have is string theory. And I'm actually working on black holes in string theory, so I'm kind of working in this kind of things in string theory, but the answer that I give you today is we don't know. Sorry, but that's the answer. Okay, so I think that's almost everything I wanted to say, but I will finish with another question. Okay, as I said, I'm a theorist, so I like the questions. Okay, so let me just describe something very fast. To simplify, imagine that there's a tunnel. Okay, this tunnel cannot exist because it would break. Okay, so just imagine like if you want a region of space, and we are here, and we are falling towards the black hole. Okay, this tunnel, it has one direction, right, which is that one, which I will call R. R is just this direction, so R could be 0 here, R could be, I don't know, 10 here, so this is R 1, 2, 3, 4, blah, blah, blah. Okay? R is just this direction. And we also have time, right? Time is passing as we are moving forward. So when you take the equations for that, you have R, which is the tunnel, and time. When you study the equations, after you cross the event horizon, what before was describing the tunnel, the space, in the equation, this now becomes your time. And what was the time, it now becomes the space. Okay? So now my question, so the thing is, once you fall inside the black hole, you cannot get out, essentially, because it's not like you're falling into the black hole. what is happening is that the future, your future is the singularity. So no matter what you do, you can move as much as you want, but your future is the singularity, is death. So after you fall in, what was describing time now describes space. So okay, as I said, I'll just say it again. Your future is the singularity. You cannot do anything to avoid that. Okay, so the question that I want to leave you with is, okay, this is a bit weird, but could you understand what happens to you as you are falling in if your future is the singularity?
Wow.
Maybe I can answer now if you want.
Maybe you understand everything in the universe at the same time, all at once.
Maybe.
That seems kind of interstellar.
Suddenly you're in a bookshelf and everything's going crazy.
So actually, Interstellar was scientifically very, very accurate.
Well, apart from
up to the ending, yeah. But before that, it was very, very accurate.
Except for the cloud thing.
What
That
cloud?
was the only thing in Interstellar, is that scene where they're on they're standing on the clouds on that planet. And once a couple of scientists came out and said, actually, it wouldn't be dense enough to stand on this, and that's therefore inaccurate.
Oh, I see. But
that's the only part.
What were those clouds
I
made
can't
of?
remember what they were, but I just remember
Did
reading.
they say? Okay, maybe
some
it can
scientists
be
came out and
said.
said it's the only thing in the whole of Interstellar, except for the last 20 minutes,
Yeah.
that's not actually scientifically accurate, but everything else is.
And the fact that the black hole needed to be much more massive.
Yes, that's also a
Really?
flaw.
Oh,
But
I didn't know that.
So the fact that the guy aged, I don't know, 20 years, it was around 20 years in a matter of 1 hour in their own time frame. The black hole needed to be much more.
But we checked that, and it's okay.
So
Instead of the mass being,
emotional
if the top mass is 1, instead of it being 0.8, it had to be 0.999. Okay, but that's still something I would allow for them.
Yeah.
I have a question. Would you recommend Interstellar?
Interstellar?
Do you like it?
Yeah, it was okay.
I think it's best to see in the cinema.
A theoretical
with his
physicist
amazing-
says, okay.
Stamp for approval. Okay.
It's one of those movies you need to see in 3D. Like, there's not very many movies like that. So that's
Well, there's,
So black holes are kind of scientifically observed, proven and observed. Are wormholes the same, or are they just theories?
no, they are just theory. Yeah.
But
And actually,
that's
wormholes.
antimatter was just a theory.
But like, they used to be
Yeah.
true because they like Star Wars and Star Trek more like half of
Is it a kind of widely held theory then, or is it a
No, so with the same theory that we have the black holes and it describes everything, that same theory has a wormhole, for example.
Okay.
But that same theory also has a white hole, which is the opposite of a black hole. So
What?
Once you get into this abstract geometry and mathematics, it gets a bit crazy.
Yeah.
I don't-
white holes?
I feel bad. I feel bad because these guys are actually physicists, but we actually had an event on wormholes with Alice Happel, and it's a really well-respected theory. Like, it's really common, and it fits really neatly with black hole theory as well as outlining. So there's a lot of ways you could, account for the ambiguity of the universe, and wormholes are one of the most compelling ideas. That's the idea I'm getting from Alice.
It's also happened before where mathematics and a theory has provided an answer to a question we didn't even know we had. And then we thought that's ridiculous, why would that exist? And then we found it experimentally and antimatter, for example, we thought it came from mathematics, Dirac, I think, and he found it, and then he was like, oh, that can't possibly exist, that's ridiculous. And then we found it and we were like, oh.
Also, before we move on from wormholes, if you want to read Alice's articles about wormholes, you can find them on our website, www.sciroom.org. Ask questions now. Anyway, Dice has a question.
So I read that information is also gone when you enter a black hole. But how does it fit into like second law of thermodynamics? Like it says like you have to preserve the entropy of the universe.
yes,
But when the information is
yes,
gone,
you need to slightly modify the second law, and then So the entropy of the universe is the entropy, I would say, of the environment, which is everything that's not the black hole, plus the entropy of the black hole. When something falls into the... Sorry. Okay. And when something... So entropy is entropy of the environment plus entropy of the black hole. And when something falls into the black hole gets bigger, and the entropy of the black hole is proportional to the area of the black hole, to the area of the surface. Yeah. So the entropy is still non-decreasing always because the surface increases, and this increase is at least the same as the entropy of the thing that was falling.
Oh, so okay.
So information is lost or not. That's quantum thing. You might be able to answer that or not, but the entropy, the second law is conserved, is satisfied still.
Okay, so the information in a way preserved in the surface of the black hole.
That's what I... Yeah, so according to this theory, no, if you start looking at quantum effects, in string theory it is conserved in the surface.
So you don't believe that gravity as quantum particles exist? You don't believe that the quantum particles of graviton doesn't exist? Because
graviton, yeah, no, yeah, the graviton exists.
Okay,
We don't know that it exists, there's no evidence. But yeah.
Yeah, but it has to exist.
If you believe in string theory, then it has to exist.
So, obviously, like scientists have a pretty good idea of what kind of stars are likely to form black holes. Are we kind of watching certain stars at the moment that we think might be about to collapse with the hope that we might be able to see a black hole being formed? Is that a likely thing we're going to see any time in the near future?
I don't think that's very likely, no. But so I don't know current observations if they have detected any star which is within reach, and it's like that. But I'm not very hopeful, to be honest.
Okay, it's
yeah, because
just because it's
so black holes, stars which are small will not form a black hole, and stars which are very massive, they will have already created a black hole. So maybe we'll have stars creating somewhere, but I don't think we are seeing this with enough precision. And
fair enough.
So I ask this to every physicist I know. So I understand that black holes, they're taking in all this matter and information. So some people say, where is the information going? Is it being totally destroyed, or is it being stored somewhere? And this idea of it being stored somewhere led to a theory that black holes could be a quantum computer, because they're storing information in a way that why is it quantum again? I can't remember, but I went to Marika Taylor's talk, and if you know her.
you sent me the article.
Yeah. So what do you think about that? Do you think a black hole could be a quantum computer?
yeah. So I would say it's not that it could be, it's that black holes are the best quantum computers that could exist.
If information is stored on external, if it's in string theory, which we do.
Yes, okay, so if information can get out, then a black hole is the best quantum computer that can exist because it's the most efficient one. And also, if you can kind of modify its shape, you can also set it so that it makes your calculation the fastest that you want, even if it's serial or parallel or whatever. You can still shape it and have the best computer. And it also has the most memory and everything. So
could we ever harness black holes to use them to mold reality?
So as a quantum computing stuff, I don't I don't get the idea. You make a computer near the event horizon.
No, but
you make a mistake and then you go on.
No, but the thing that you could do is, okay, I don't want to scare anyone, but in particle accelerators, if some theory is true, which could be, then there's a chance that after two protons collide in a very, very, very high energy collision, a very small black hole forms. So not a black hole that would swallow the Earth or anything, just something tiny that will evaporate in a fraction of a second.
So when they were about to turn CERN on, certain tabloid newspapers got hold of it, and there were actually people who were seriously ranting on the internet and trying to sign petitions saying, do not turn this thing on, it's going to suck, you could destroy the world. And the physicists were like, oh my god, this is just the most remote possibility. it's just stupid. But yeah, that's
no. So according to the theory, some very, very small black holes could be created, but this would evaporate instantly, so nothing would happen there. And actually, now that you say this, in Fermilab in Chicago, in the United States, they built a particle accelerator, and to prove to the people that this was not dangerous, they put buffaloes living on top, and now if you go there, you can say, oh, I'm going to see the buffaloes, and they allow you in, even though it's like a national security place, but they allow you in to see the buffaloes. Say, okay, if the buffaloes can live, I also can live 10 kilometers away from it. So, yeah. But there's no worries of a black hole being created in those places and eating the Earth. That's not going to happen.
As a theoretical physicist, do you sometimes feel in your career that you are working in a very delayed gratification basis, that you come up with different experimentations, different approaches of trying to explain certain chains of events, and to only then find out they were wrong, or to only find out they were quite true, but a lot of time later. How do you cope with that?
Well, but doing something which is half true, half not, close to the truth, and then you see, oh, but I have a new observation now, and it doesn't kind of fit. That's what gives me a job for the next couple of years, right? So I'm happy about it. Yeah, and no, I mean, you do the best you can. You have your mathematical theory, you do with the observations the best that you can, what makes more sense, and with this, the simplest or whatever. And then you're doing the best that you can. Of course, anything that I have explained is not the final theory. At some point we'll get some observation and we say, okay, what we're saying all is very nice, it works very well, but there's this thing that if we do this thing in that weird way, in that weird place in space, your theory doesn't work, so we need a new one. Okay, my theory was still able to... Yeah, so for example, general relativity, it can seem very abstract, it can seem very weird, but without general relativity we would not have GPS, for example. So a GPS without the general relativity corrections, I think that within 2 minutes it's already out of range, and I think that each day the radius of error increases by 10 kilometers. So, okay, we are doing these things, but these things can also later be applied to other things. So, still we are doing something profiting sometimes.
I had a question, but I've decided it's too technical. I'm going to ask you after because no one else will care.
Okay. Does anyone have any closing, non-technical, boring questions?
Yes.
I was wondering if the closer you get to your future, you've described that you're sort of being split apart into your component pieces, but then at the same time you're not also being crushed together.
Yes. So yeah, what I wanted to say at the end is, as I said, the black hole, so the singularity, when you fall, it becomes your future. So the way I see it, it's not like you are falling somewhere. Since the singularity, since the center, okay, it has no center because time becomes space and space becomes time. So there's no center, right? But everything that falls into a black hole, as I see it, space-time itself collapses around each thing that falls in until it closes. And you were in the middle, so it closes with you. Yeah.
So if it's a singularity, wouldn't it violate the law of conservation of matter and energy? Because
well, it depends. So I think when I say singularity, it means I don't know what's there.
Okay.
Yeah. So as I said, with this theory, the way I see it is that just space-time collapses, and it disappears, it violates something, I don't know. But to really know these things, we really need the quantum effects there are very, very strong. So we really need the quantum effects. So when I say here singularity, what I'm saying is, okay, this theory is classical, there we have something that we don't understand. And that to understand that something, we need the quantum theory. Okay? And with the quantum theory, there's some explanation, and then nothing is lost, there's no infinite, and things more or less work. So there's no violation of anything, there's no matter or energy violation, or everything stays there. Yeah.
Okay, I think this is a good bit to close the main event. Thank you everyone so much for coming, and please thank Joan for his amazing talk.